Zero-knowledge proofs enable a single prover to verify thousands of transactions without ever exposing the underlying data. But if you're building a new protocol and you blindly select a ZK framework, your architecture will fail when it hits the real world. Right now, the space is dominated by two competing systems, ZK SNARKs and ZK STARKs. If you just read the mathematical white papers, both promise incredible scalability. But white papers don't run code. When you actually deploy these systems, you hit brutal physical constraints. To figure out which one you actually need, we have to look at recent empirical testing, not theoretical benchmarks on supercomputers, but how these systems perform on standard consumer hardware. The data reveals a specific trade-off. You have to choose between compact proofs that generate in milliseconds versus trustless security built for massive verification scale. Understanding this hardware trade-off is the only way to successfully match a ZK architecture to your network's specific bottlenecks. Let's start with proof size. If your protocol lives directly on a layer 1 blockchain, storing data on-chain is expensive. Every byte translates directly to gas fees. ZK SNARKs bypass this by using elliptic curve pairings to compress information. This chart shows the empirical proof size for SNARKs. It consistently yields a proof of just 384 bytes. But ZK STARKs rely on Merkle trees, expanding proofs to 68.5 kilobytes, a 123 times difference in size. Operationally, pushing 68 kilobytes per proof to a layer 1 will significantly increase user costs. STARKs generally require high bandwidth environments or off-chain data availability layers to function economically. If your application lives entirely on an L1, where every byte dictates cost, proof size becomes the primary factor for your architecture. Storage is only half the equation. We also have to evaluate the prover, the machine generating the proof, to measure generation speed and CPU memory load. SNARKs get a computational head start here because they use pre-processed structured parameters. Much of the heavy math is solved in advance. That head start pays off. On an Apple M1 chip, SNARK proofs generate 68 times faster, clocking in at just 55 milliseconds. The hidden trade-off is that intense curve math creates violent transient memory spikes that heavily stress a system's garbage collection. STARKs don't have that pre-processed advantage. They have to run full polynomial interpolation at runtime. This makes STARK generation slower. On the exact same M1 hardware, it takes over 3,800 milliseconds to generate a single proof. It also requires large, sustained memory buffers for its recursive rounds, which places a heavy and constant toll on the physical hardware. Consumer devices demand the speed of SNARKs for a functional user experience. STARK prover duties generally have to be relegated to dedicated servers. Transitioning to the verification layer, we find the metric that dictates a large-scale network's total throughput. STARK verification relies on lighter, hash-based primitives that leverage native arithmetic, rather than heavy curve operations. This quadrant chart plots memory load against verifier speed, revealing STARK's counterintuitive advantage. Despite taking much longer to generate, STARKs verify faster, just 472 milliseconds on an M1, compared to over 1,800 milliseconds for a SNARK. That rapid verification speed makes STARKs highly efficient for massive batch processing and parallelization. For L2 rollups handling thousands of batch transactions, superior verifier scalability easily offsets the initial sluggishness of proof generation. Finally, we have to look at the non-hardware constraints, the differing trust assumptions and long-term security profiles. ZK SNARKs require a trusted setup. This introduces a centralized point of failure. If the parties running the initial ceremony don't destroy their toxic waste data, the network can be compromised. SNARKs also rely on pre-quantum cryptography, leaving them theoretically vulnerable to future quantum computers. ZK STARKs skip the trusted setup. Their collision-resistant hash functions provide complete algorithmic transparency and post-quantum security right out of the box. To reach this level of trustless post-quantum security, a protocol must be willing to absorb the massive storage and memory costs inherent to the STARK framework. With the empirical data clear, we can map the right technology to specific developer profiles. First is the L1 Smart Contract Builder. You operate in an environment where every byte of on-chain data is a direct financial penalty to your user. You need ZK SNARKs. A 384-byte proof size is a non-negotiable requirement for gas efficiency. Second is the edge or mobile app developer. You are building decentralized wallets or applications where the user's phone has to physically generate the proof. You also need ZK SNARKs. Generating a proof 68 times faster with lower sustained memory is mandatory for a functional mobile experience. Third is the L2 rollup architect. You are tasked with batching thousands of off-chain transactions into a single verifiable proof to scale the network. You should use ZK SNARKs. The superior verification speed easily justifies bulky proof sizes when those costs are amortized across thousands of transactions. Finally, the security maximalist. You are an institutional architect securing billions in value, and you cannot afford the reputational risk of a trusted setup. You also need ZK SNARKs. Post-quantum resilience and total transparency mean you will have to invest in the heavy-duty infrastructure to manage it. Neither framework is objectively superior. A successful architecture depends entirely on acknowledging empirical hardware limits and aligning mathematical trade-offs with your physical constraints.